Hey guys, welcome back. So today in this video, we're going to be talking about one of the tweets I posted on Tuesday. So if you follow me on Twitter, you may have seen this. And if we go over here, you can see I basically tweeted that I was working on my own kind of basic bare bones debugger for iOS devices out of curiosity for how debuggers work in general. And in this video, I'm going to show you guys a kind of a live demo of this debugger, showing you guys how you can actually run it and install it yourself, because the source code is now available actually, as you might have just seen on my GitHub page. And I'm also going to be covering a couple basic tutorials on how you can implement some of the features I've included in this if you are also interested in how debuggers work. So this kind of fits in with the part of the iOS security playlist on this channel. So anyway, first of all, I'm going to show you guys a live demo of what this basically does at the moment and what features I've currently implemented. So it's very, very basic. That's why I've sort of referred to it as a bare bones debugger. It doesn't have any kind of real debugging functionality at the moment. So there's no ability to set breakpoints and to actually step through program execution instruction at a time. But it does have some basic functionality that I want to show you guys. So here I'm SSH'd into this iPhone 5C right here. And I'm going to just run a test binary. So I'm just going to execute a test binary. And we can see that that is running here. So you can see the PID, the process ID is 2070 for this test app. Now this is just a very basic binary that's just doing an infinite while loop, just so it stays running for the purpose of testing out this debugger. So we just need to remember that. So 2070. And then we're going to execute the Lyla debugger, which is what I've named this. And we're going to do a -v for verbose modes. This will give you some more information about what's happening behind the scenes. And we're going to run this, and you can see it will print out a little welcome message, and it asks you to enter the process ID that you want to attach to. So at the moment, basically, you can attach to any process that's currently running on the device. There's no ability to actually choose the path to a binary file to then execute, but that's easy enough to implement, so I'm going to add that at some point. But for now, you just need to know the process ID of a running process. So as I said, we're going to put in 2070 for that test binary. And it should say attaching to that process ID, and it will give you the task report for it if it did succeed. So from here, we can basically execute commands just as you would within a command line debugger such as GDB or LLDB, but obviously with much fewer commands at the moment. So first of all, just execute help to actually print the list. This gives you a list of all the commands that are available at the moment. So you can see, if we just stretch this out a bit, see the description of each command. So we have help, prints this help message, we have read, and we have a write command to allow us to read and write from the process memory space. And you probably already know how this works if you've seen my other video on using VM read and VM write, the Mac API calls. But go ahead and check that out if you want to see how that's been implemented. Then we also have register access commands. So registers will print out all the list of the current register state of the program. And then reg set allows you to actually set a value for a specified register. And then we have suspend and resume, and then quit. So this will just exit the Lyla debugger. So I'm just going to show you guys basically walk through all of these. So first of all, we'll look at the registers so we actually can see some addresses before we begin reading and writing from it, because otherwise we'll be basically guessing addresses. So we're just going to type in registers and then enter, and you see it will give you a register dump, which prints out all of the ARM registers. Now at the moment, this is actually, or the version I put on GitHub is only for ARM v7, so 32-bit. So it's easy enough to basically pull this over if you want to use this on 64-bit as well. Only some minor modifications are needed, but for now, the one on GitHub will only give you sort of a list of the ARM registers, the 32-bit. But it gives you all the way from R0 up to R12, and then it gives you the LR, SP, PC, and the current program status register. So we'll just use this to actually read and write from a basic memory address. So if we take the stack pointer value, which is currently this value right here, and we can read what is currently there. So we type read, copy, paste that in, and then we want an amount that we're going to read. So let's just say 20 in hex, and it'll print out memory from that address. And you can also then write to that address. So if we do write that same address and then put in a custom value, so 414141, and that will say, you can see it wrote the bytes successfully. And if we just rerun that first command, you should be able to see that we have the new bytes, the 4141 bytes at that address. So the reading and writing does work just using those two basic commands, so it's easy enough. We can also set the register's state, as I said. So let's just do reg set, and then let's say R1, for example. And then we just want to put a custom value, so we'll put another custom value here, so 424242. And then if we do registers again, registers, and you can see R1 now contains the value 424242. And also you can suspend and resume the task. So you can just type literally suspend, and that will pause the execution of the task. So it's now sort of in a pause state. All the registers values would stay the same, so it would not be continuing to execute instructions, and then resume would undo that and continue it running. So for example, you could pause it and then you could mess with the registers and change like the PC to something else and then resume. And once it's resumed, the PC is going to be pointed to a new instruction, so it could take a different path. But that's basically all the functionality I've currently got implemented with this. Yeah, as I said, pretty basic at the moment. There's no kind of real debugging functionality in terms of stepping through the program or setting any kind of breakpoints, but I am looking into how that all works at the moment, so maybe I'll sort of push some updates to that on the GitHub version. So as I said, if you want to look at the source code, then it's available on this my GitHub repo, so I'll just post a link to this in the description. And also, if you want to actually run this on your device, then what you need to do is just compile this C file and then add the entitlements that it lists here, so the standard sort of ones to allow you to use task for PID. And as long as you're running as root, you should be able to use it exactly as I just demonstrated in here. So for those of you who actually also want to learn a bit about how this is implemented, I'm going to cover in this video how you can implement the register reading and register writing part of this debugger. And then the rest of it is pretty much self-explanatory, as well as the fact that I've actually covered the VM read and VM write on another video. So if you want to see how that works, then check out the other video, which I'll also leave in the description. But yeah, so for the rest of this video, I'm basically showing you guys how I implemented the register reading and register writing in this debugger. So we're going to create a new basic program that's going to do this for us. So we'll just call this test on the desktop. It's not a desktop. Okay, and inside here, we're just going to include some of these standard headers. Basically just copied and pasted that from here. And we're going to have a very basic program. It's not really going to give you any kind of input on what you want to change the registers to do, but it's just going to be kind of demonstration of how it would work. So inside the main function, we'll just start by printing out the, or actually attaching to a process first of all, and then printing the list of registers for the main thread in that process. So we obviously do need input for the actual process ID because that will likely change. So we'll just first of all ask enter PID, and then we'll just scan that into using a scanf into an int variable that we can then use later. So use the %d format specifier and then the PID variable. And then we need to just basically call task for PID with that PID to then retrieve the task port for that process, which then gives you the ability to basically do everything that's been done with the debugger here. You have all this functionality just from having the task port, as you can see I've done up here. So I'm just going to copy and paste this from here, just to make it easier for the purpose of the video. I'm going to paste that in there. So essentially we're going to do a bit of error checking as well, but we need a kernel return type, which we're going to name as KR. And then we're going to set that equal to task for PID, pass mac tasks or mac task self, the PID, which has been entered by the user. And then we also need a muck task port or a muck port type to basically store the port from the process ID specified. So, and then we basically check if this does not equal kernel success, and we have an error. So you can just print out error there, and then we don't need this bit because that's part of Lyla, and it would basically exit at that point. If not, then we have the task port for the specified process. So from here, we're going to obviously print the register state. Now, the way we did this is, first of all, we need to actually see how many threads are in the process. So for the example one I just did with the test process, there's only one thread in that, which was just the main thread, so I just read them straight off that. With other processes, you're likely to have more than one thread running at the same time, in which case they all have their own set of registers. So you need to kind of choose which one you're going to decide to print. All right, so I'm going to split this up a little bit. So we're going to have a function for printing the register state. So we'll just call this print reg. And this is going to need to take in the muck port for the process we specified. Otherwise, we won't be able to use these functions. So we're just going to do it like that. And we'll pass that from main in a minute. But first of all, as I said, we need to get the number of threads in the running process. So we're going to create a thread act port array type. And I'm referring to a very good article about known as replacing ptrace, which I'll also link in the description. This is where I actually found out about this specific ability to read and write from registers. So I'll leave a link to that because that's definitely helped me a lot in this. We're going to call this thread list, and this is going to be basically an array of all the threads in the process. We're also going to need a muck message, or MSG, sorry, type number T, and we'll call this thread count. And this is going to also give this basically just a number of how many threads there are going to be. And then we're going to call the task threads function. We're going to pass in the port that we would have got from the main function, which we're going to do in a minute. And then we're also going to, by reference, pass in thread list and the thread count. So if this call succeeds, we should have all the threads listed in this array here, and we should have the number of them listed right here. So basically, to keep this video as simple as possible, I'm going to assume that the process only has one thread running, so that we can just stick to that. But if you have aims of making some kind of complex debugger, then obviously you're going to need to account for possibility of having more threads running in one process. So now that we've got that, we're going to now create a struct arm thread state T. Now this is where you will have differences depending on the architecture. So arm thread state T, we're just going to call this arm state. This is for a 32-bit ARM device. Now you can actually do this on anything, not even ARM devices. You can also do this for OS X as well. And but this struct right here is, you can see here, it contains, if we click on this link, it contains these variables inside it. So we have an array for the R registers. So from R0 up to R12, we have an array of those. And then we have separate individual integer variables for the stack pointer, link register PC, and the current program status register. So this struct, basically, we're going to pass this into a function. It's going to retrieve the register state for that thread, and it's going to basically populate the struct, and we can then read out the register values from that. So we're going to create that. We'll just name that as arm state. And we also need another one of those muck message number types. We'll call this SC. And this is going to equal arm thread state count. Okay, so we're now basically set up. All we need to do now is call the thread get state function. So thread get state. And we're going to pass in the thread list and then reference what thread we want to use. So it's going to be the first thread, so index 0 in this thread array. And then we're going to put in arm thread state. Then we're going to cast the actual arm state to a thread state type, so thread state T. And then arm state by reference again, so we can actually populate it, and also the that SC variable. So once this call basically succeeds, it's going to go to the first thread in the process that's running. It's going to populate that structure, giving us the ability to read out all of those register values. And then after that, it's simple enough to just basically use print them out onto the screen using printf. So the way I did it with Lyla, what you can see in here is we basically had a long printf statement that formatted it in kind of a nice way where you could see it says R0 and then it prints out the actual thing. So I'm just going to copy and paste that whole printf statement from the Lyla source code and paste it in here. So you can see this formats, it prints out all of the register values and then it accesses them after in the actual arguments here. So you just basically access the arm state structure and then do a dot. And then if you want to access either one of the general purpose registers, then you do __ R, and then in square brackets, you just reference which register that is. So for the first register, R0, it's going to be at index 0. That goes all the way up to 12. Then we have individual variables for the link register, stack pointer, and program counter, as well as the CPSR register. So you just register that all, reference that all like that, and then that printf statement should work. So we're not going to test this yet. We're going to complete the whole program first, but I'll run this afterwards. So for setting the register state, it's actually a similar process. We also need to basically just use the opposite of thread get state. We use thread set state, which allows us to create our own structure, modify the actual variables within inside it, and then set the state for a specified thread to our modified structure. And it will basically update that in the running process to have a new set of registers depending on what values we set to it. So actually thinking about it, it's going to be simpler to just keep this all in one function instead of having a separate one for setting the register values, because otherwise we're going to need to basically repeat all this code and re-get the state and stuff like that. So we're just going to do it underneath here in the same function. So it's very, very simple to actually set the state. All you need is to actually, obviously, first of all, get the state from the specified thread. And then you can modify the struct in any way you want. So it's simple enough by just doing arm state dot and then the register you want to modify. So we'll just go for the PC. And then you just set the value to a new value. So we'll just go for 414141. and that's now been updated in that structure. And then we just need to call basically the thread set state instead of thread get state, but it takes in the exact same arguments in the exact same order. So we're just going to copy and paste that line, and wrong line. So we copy and paste that line and just change that G to an S. So now it's going to be thread set state, and it's going to set the state from the first thread in the process, and it's going to basically push our structure into that thread, and it's going to have the updated register value for the PC as 414141. So the process will now try to jump to 414141 and obviously terminate. And then if you actually want to check again after you've updated the register state, we can just recall the thread get state and then reprint out the register values to see a change. Now, actually at this point, because the process will still be running, and since we've modified the program counter, it's going to actually crash and exit. So this will not actually work unless you terminate the process, or sorry, not terminate, pause the process, so suspend it, which was one of the functionalities that you guys saw at the start of this video, where I added the command to terminate or to suspend. So where's that gone in here? Yeah, so we're just going to suspend the task at the start before we actually mess around with the registers at all. So right at the top here, we're just going to suspend it, which is going to put it in that kind of paused state. So the registers are not going to be changing because the program is just paused. It's still running, but it's not actually executing any code. And then after we've messed around with the registers and read them back out, you can resume it again. So task resume and pass in that task port for the process. So this should work. This should, if we recap, I actually need to also call the function from here. Sorry if you can't see this due to the face cam. I'm just going to quickly call that. Okay, so we call print reg, pass it in the port, and this code will execute. So as a recap, it's going to get the state from the main thread in this program. It's going to print out all of the registers, all of their values, and the program at this point will be in a paused state. Then it's going to set the program counter in our structure to a random value, and it's going to update that state of registers. So the program the process is now going to have a new set of registers with modified values, and it's going to print them out again to confirm that we did modify the value of the program counter, and it's going to resume the task, which will basically cause it to crash. So I'm just going to quickly get this over to my iPhone 5C, compile this, and show you guys that it does work. All right, so we've just compiled that, and we have some warning, but we're just going to ignore that. It did still compile without any errors. And we also obviously need to sign it with the entitlements for task for PID. So I did leave them in the comment at the top of this program source code. So you want to put this into an XML file or a plist file, and then just use ldid. So ldid-s, specify the name of the file. So task for PID or tfp.plist, and then sign that binary. And yeah, so as long as you are running as root now, this should work. So I just noticed one small issue with this. When you're actually setting the state, you don't want to pass the sc variable by reference. So you don't want to have the 10% here. So just get rid of that. And that should work. I did just try just now and it didn't work, but yeah, that was the issue. So we're just going to do that again. So I have the test binary running now. We're going to run the top command to see the process ID again. So 2306 this time. And we're going to run test, enter the process ID, so 2306. And this time you can see we have the register dump output, so just as it would be from Lyla, as we did copy that exact code. So it just prints out all of the register states, and we can see the program counter is set to a legitimate memory address. And then we have it printed out again after we've modified it, and you can see this time the program counter is set to 414141. And then it does obviously resume the task at the end of this function. And the program did just crash with this segmentation fault 11, so that does indicate that it was trying to jump to this address. So that's basically how the register manipulation was implemented in my own Lyla debugger thing. This is actually a lot simpler than I thought it was going to be. When I was first looking into this, I didn't know about these simple functions, thread get state and thread set state. I was thinking I was actually going to have to look into using the kernel memory and actually looking into the sort of the task structure in the kernel memory to read these sort of things. But it turns out it's actually very, very simple. So thanks to the guide that I mentioned earlier, which I'll also leave a link to in the description, I was able to do this and implement this into Lyla debugger. So if you want to download this, as I mentioned previously, go ahead, go to this link. I'll leave a link in the description. Download this, compile it on your device and check it out. And also be sure to give me feedback on it, or try and even implement your own features if you know anything about the actual breakpoint setting and stepping through instructions, that sort of functionality. Then I'll be interested to know how that could be implemented, because at the moment I've looked into a few ways that people do that, but I've not actually come to a conclusion on how I'm going to implement it myself yet, but that will come at some point. So yeah, anyway, I hope you guys enjoyed this video. I'll leave all the links in the description so you can check out anything you're interested in. And yeah, that's pretty much it. So hope you guys enjoyed. Thanks for watching. Don't forget to subscribe for more, and I will see you next time.